All right.
It's like
What am I
going
doing?
back to Paris.
Yeah. All right. Good idea.
No, this time I'm going to Russia.
Oh no way. Yeah, no way. Let's see, where were we last time? Wow, this is the smallest audience we've had. You think this is it? Oh, wow.
I'm wondering if you were going to do a test review.
Yeah, well, so, I mean, oh no, I mean, no time, there's no time. We have office hours. No. I mean, the thing, so I guess, welcome to Stochastic Control. Hi, Florence. Hi, Sergio. Sergio in Cambridge, a friend who plans to watch this. I'm not giving a review now, there'll be office hours, but I'm going to, and there's no MDPs in the exam tomorrow, but the material I'm covering, basically the techniques are stuff that you'll be using in the exam. Okay. But so first of all, remember this linear program. So basically, to solve the average cost optimality equations, we had value iteration, policy iteration, and this linear program, and that's that. The linear program is valuable because you can append constraints. Okay. So basically, I mean, come on, help me out, somebody. I could have some energy costs, but I could have a cost on stress to this airplane. There might be another cost that has to do with the amount of jittering that I'm doing. I have a whole bunch of other constraints I'd like to be satisfied. All right. And so putting in these extra constraints is still a linear program, so you can solve it. Okay. So this set G here is a convex polyhedron, and the vertices, it's so cool, are precisely the situation where phi is deterministic. So it's equal to either 1 or 0. So it's a degenerate probability. It's not a randomized policy, it's deterministic. So you would just call this phi of x. So basically you would just denote this as delta phi of x. I know that's a horrible abuse of notation, but that's what we've been using so far, phi for deterministic stationary policies. So I'll just erase that. So what do you think happens here? So if you put in constraints, what would the optimizer look like? Anybody have a guess? Well, think about it like this. If the optimizer doesn't have equality, then the constraint wasn't needed anyway. You could throw it away. So if you optimize this and all these are strict inequalities, then you might as well get rid of these constraints, and we know the optimization is deterministic. Okay. The other extreme, suppose these are all equality, right? Well, then in order to make this true, I have to move my gammas around in order to in order to satisfy these equality constraints. And it's really unlikely that of these finite corner points, one of them is going to actually have all equality constraints. You know. So what you can show is that if there's m constraints, that phi star of u given x has at most m points of support. So what does that say? It says that phi star of u given x is equal to 0 for all but at most m points u. Okay? All right, so those u's for which this is positive are going to depend on x, obviously, right? And I'm not saying there's only m u's you'll ever choose. That would be ridiculous. But for every x is at most m. Okay, so that's convenient. Okay, so basically the LP approach allows for extensions. For me, it's mainly for analysis, and also again, I was saying I have hope that the LP approach might be one of the most powerful approaches to approximate dynamic programming that hasn't been explored enough. Okay, all right, so I talked about the dual, and I'm not going to find what a dual is, but if you know about linear program, an LP has a dual, and without these auxiliary constraints, that has a dual as well, but forget that. The dual of this basic thing turns out to be this. It's maximum over eta subject to, and then let me use my notes. And so basically, this is a dual after a lot of work. And I mentioned last time a Q function pops up. It does, but forget it. The variables here are the constant eta that appears here, and this vector h that appears here. So I'm maximizing over all eta and h. But my objective function doesn't depend directly on h. I just have an eta here. So basically, that's it. Once you write down what G is, I'd have to write it all down again. I'd have to explain what a dual is. I'd have to go through a bunch of algebraic mess. But in the end, that's what I get. The dual of this LP is that.
What does that mean, max eta with eta and h?
Because those are my variables. So when you have a linear program, you have to specify the variables. So the variable is eta. That appears in the objective function, but not h. But it does appear in the constraints. I'm maximizing over all eta and h. The quantity eta, so give me any h and eta. It's feasible if this inequality is satisfied, and I take that eta, I stick it in, and then I maximize it all eta. It looks totally backwards, but here we're minimizing something, and in a dual you always maximize.
Okay, so that other eta, we can get rid of it now because we have eta and h.
No, eta and h are the variables.
We're maximizing over.
So h, is like think of it as a column vector, and eta is a scalar. That's a vector we're trying to optimize over, right? So the general linear program is to maximize C transpose x, subject to, say, ax is greater or equal to b, say. All right. C doesn't have to be all, C can be degenerate. One possibility is C is equal to 1, 0, 0, 0, ... 0. And that's what it is here, because my x is equal to eta and then h.
Okay. Why do we want to maximize the average cost?
It would not. So that's what I want to talk about. So I said that today's lecture, even though there'll be no MDPs on the exam, the analysis of this is just straight out of the course. So how would we analyze this, everybody? Yeah. So you're right, it looks totally backwards, but don't forget that. The inequality is backwards. So we've been having a lesson sign. This is our pH, and it's greater than h. You know, put the h to the side. So everything's screwed around. It's all backwards.
It's almost like the Poisson inequalities.
The Poisson inequality backwards is what it is. So exactly that's the analysis. So you give me a randomized policy. And again, there I'm allowing randomized policies. I will here as well. So if you give me any randomized policy, my notation last time was to say p phi x to y is this sum here. Because for given x, I'm saying what's the probability so I'm going to flip a coin. So given x, I'm going to have a bunch of u's I'm going to choose, through some multi-valued coin or dice. Randomly pick the u, and then I've got the probability given that u of going from x to y. All right, so if this is true for all x and u, you see u only appears here, so I can actually take this phi and multiply through and sum. Okay. And let's put arrows going backwards. Really, this constraint, written in the sort of linear program framework, I can change notation, and really what I'm saying here is that this inequality holds for every randomized policy phi. So it's if and only if. Okay?
This is by definition almost our...
Well, yeah, because here I can, if it's true for all x and u, basically I can pick off every deterministic policy. I can pick off, it's the same. Think it over. It's exactly equivalent. So going from here to here is just summation, and then saying that if this is true for all phi, I can take the phi's to be degenerate and get this for every x and u. And then we know what to do, right? Write this in a more convenient way. P phi h is greater than or equal to h minus c plus eta. And you know where I'm going now. Like this is fair game on the exam now. Because we've done this 100,000 times. So we know.
Hit both sides by p.
Yeah, and I'm not going to do it because you've seen it too many times. If I'm going to just jump straight to what we know, the nth, if I keep hitting it by p phi, I'll get a sum. And this is a constant. It just gets added on over and over again. So you get an n times eta. All right. And then if you remember the program, you divide by n. And so what you finally get is that I can take this to the other side and fool around. So what I'll call eta sub phi, maybe of x, so you have to remind yourself what limit infimum is, okay? So this is a bunch of points as n goes to infinity. it might not converge, but there's a limiting lower bound. And then you see what happens is that that average is greater than h over n minus that. Keep it between my hands. And then those cancel, and you get an eta. And there we go. So given, and so that's the thing is that, so I forgot the lim inf. So we're in a finite state space, okay? So h is bounded, p into the h is bounded. This whole thing goes to 0. So this is actually equal to eta. And so that's what's amazing, is that given any feasible pair, so you give me any eta in h that satisfies this inequality, it is a lower bound on this lim inf for every possible policy. And that's the question. That's the answer to your question. So this is a lower bound on performance for every policy, so that's why we maximize. Now, I'm not saying that's what we're doing here. This linear program is the dual of this linear program, but then we could have worked this out independently, you know. So there it is. Okay, so you punch this into MATLAB, you get an answer. And actually, it'll be fun to do this. I've never asked anyone to do this before, but we should see what's fastest. I mean, is this faster? Is this LP faster than value iteration and policy iteration? How good is the MATLAB or Python solver? It might kick ass. I've never tried. It's really funny. It's just computers have just gotten so fast so quickly, you know. And the last time I taught the course was 2017. There was I don't know. There's been a 25% speed up since then. But when you solve this, so you solve this LP, you're going to get an eta star, 8 star, and so basically what you're saying here, this is true for all, oh, I forgot the U, didn't I? Forget it. Let's see if X here. There should be a U here too. Forget it. I meant to put in a U. I've done this just for the case where the cost doesn't depend on U. That doesn't matter. Basically what you get is that 8 star solves the ACOE only almost everywhere. With respect to gamma star, where gamma star was the optimizer for the primal. Okay, so that means that basically, with respect to the optimal policy and the invariant probability mass function for the optimal policy. All right, so it won't solve when you put this into MATLAB. You might not get equality everywhere. You only get equality on this tiny subset, which is interesting, you know. But that's all you care about anyway, because you get the policy. Yeah. Because gamma star is a graph. You know, remember, I told you that when you optimize the primal, you know you're going to get, you can, without loss of generality, get one of the extremal points. And if you're using the simplex method in linear program, I mean, you will get one of the extremal points. And so this guy is not randomized. It's just 1 or 0. So it's really just defined by a state feedback policy. So the support of this optimal guy is only a line. And so we're only satisfying the ACW on a line, but that's all you care about. That gives you the policy. I'm emphasizing this because it's going to come up in reinforcement learning later on. So I'll come back to this point later. I feel every lecture I mention reinforcement learning. It's not that I'm anticipating it so much. It's just that this will be important. There's a philosophical question we have to address about exploration and all that stuff. Because in learning, you really want to find that curve. You know. Yeah. Okay. Happy? All right. So you can use an LP if you want. So normally in this course, you guys are tortured with having to go through and watch me derive the linear quadratic Gaussian case. And I won't do it. I just won't do it. So I'll let you watch that on YouTube if you want. You know, you know, that's one of the few cases you can actually solve explicitly. So. Okay, so LQG, and by the way, it's not really LQG, it's just xk plus 1 equals AXK plus BU k plus some disturbance, say, and this is just IID, zero mean, and finite variance. Okay, and then the cost is quadratic. All right, so what's cool about this is you solve it. The only thing that's cool about this, the only thing I'm going to say, is you solve this, you'll get an H star of x, which is x transpose px, where p is greater or equal to 0, okay? And this was all done here in Florida by Coleman. And p doesn't give a damn about this. So the noise is irrelevant, okay? You get the same solution. The distribution is, so saying LQG is really misleading because you don't need Gaussian, you don't need anything. You just need ID with a finite second moment. And the distribution doesn't matter. Yep.
You're looking at the
What's that?
total cost?
Oh, this average cost. This was all average cost. All right, and which is a great segue into what I want to say next. So I really felt I let you down on the first lecture on MDPs because what happened is I wrote down the DP equations and then I suddenly launched into derivations when I wasn't prepared to, and because I usually have a different approach. I'm going to do that now. So I'm going to go through and carefully derive the DP equations through a hack. Okay? Okay, now, I might not have time. Okay, so I might let you down once more. But I know that any one of you, given 20 minutes, could derive the DP equation for this problem. You know, because you can see, you know, the first term, when k equals 0, it just comes right out. And then you have this, I mean, it's so transparent for this particular problem. All right? And the question then is, who cares? So this is easy. If I have time, I'll show you. Yahoo. All right, and this is what's fun, is it turns out that every single optimization problem you'll ever care about is this. There's nothing else. No.
For this, do we not need to know the initial input as well?
No, that's the Q function. No, this is the definition of it. No, this is dynamic value functions. It's always a function of x.
But we don't condition on the initial input?
No, we don't. We never did. No, look at this. This value function doesn't depend on. No, this is. In fact, anyway. So no, this is what we always do. All of our stuff is like this. Look at the discounted cost problem, which we'll come back to in a second. We were only conditioning on x. There's no u. There's something called the Q function we'll get into, where you condition on u as well. That's different. Okay. So example 1. So there's an example. So this is this. So anybody can see why? It's not obvious. So how can I make that finite sum into an infinite sum?
Representation
It's a crazy representation.
and using the stopping time.
Oh, I don't know if you need anything important like that. No, it's just a representation. You're going to have to cook up some new Markov chain in order for this to be this. It's going to have to be some, you're going to have to muck around with this. But the main point is that you're summing up to s minus 1 here. No, just before you reach the set s here. And notice that I'm saying I'm only going to look at this for s and s. Things get complicated if you look at start in s. I don't want to deal with that. And then I've got this here. I have a cost when I reach this, and I'm calling it v0 to remind you about value iteration. It came up there when you look at value iteration. But this is like the cost when I reach the top of the hill, if this is like a hill climbing problem. So what am I going to do? I'm going to find a new Markov chain. So create a new a graveyard state. Okay, that's too hard to draw. So what do you want to call it? I don't know, Z, the last letter in the alphabet. Okay, so Z means you're dead, okay? And now I have a new Markov chain, which is once I reach S, I go to the death state. So I'm just modifying my Markov chain. So that's why I'm saying let's not start in S, because then I'd get into trouble. And modify the Markov chain that from the death state, I go to, from any point in S, I jump straight to death, I die. And the probability of staying dead is equal to 1, And that's it. And then the cost of being dead is 0. And you agree with me, I'm done then. So you just modify the Markov chain. So what this says is that once I've got the DP equations for this total cost problem, I can just say, well, this is just this if I modify the dynamics. And so you get a DP equation like that. Yeah? Is it clear? Right, because after here, after I reach the state S, I jump to Z, and so all these terms are 0.
So they're equivalent. The first one for, like, assuming you have these things.
Yeah, I changed the model. So remember, we're just trying to derive an equation. So I'm allowed to say, you gave me P, well, screw it, I'm going to modify your P in this way. I'm going to create a graveyard state, and then derive the DP equations for the new transition kernel.
And that's when they're equivalent.
And then they're equivalent. That's right. So you'll get some funky DP equation, and then once you have this, it's a matter of just writing down the DP equations with this new transition matrix. Yeah, yeah, and that's another okay, so this is more tricky.
Do we have any
What?
functions like cost is finite or something?
Well, it's not. I mean, here, this could be infinity everywhere. Yeah. So basically, provided this is not infinity everywhere, what's the minimum, right? And here's an example where it typically won't be. Yeah. And here's another one. What am I going to do now? This is fun. Now you're not allowed to say that this is the cost, and you're not allowed to call beta to the k a state, because then we lose everything. We wouldn't be in a finite state space. I mean, no, don't do that. We're going to create a graveyard state again. All right, but there's no S. So when will I jump to this graveyard state? That's the question. Yeah. There's no way you guess. If you what?
With probability beta.
Oh man, you're good. Okay. So I'll explain to you what I mean by this in a second, but it's exactly what you're saying. So introduce a random time, which is analogous to this thing here. But in this case, it's completely independent of everything. And basically, if I look at the probability that t is greater or equal to k, it's going to be my beta to the k, which is, and so given everything, so given x0 dot 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 xk, u0 dot 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 uk, that is independent of all this data, and it's just equal to beta to the k. So it's geometric. And so what's IK? IK is that. I don't even need the graveyard, in fact. IK is equal to the indicative function that t is greater or equal to k. And then you'll see that this thing here, the expectation of that product, so you all know the expectation, the indicative function is just the probability. And so then you've got it, because basically then this is just equal to the same minimum, but the sum can go outside and inside, they commute, right? If C is positive value, it's called Fubini's theorem. And so the expectation of, because these are independent, there it is.
You introduce a random time, like, is that you can show that with the probability of t greater than or
No, it's an assumption. I can do whatever I want. So, all I'm trying to do is argue that everything can be posed as a total cost problem. And so basically, by this trivial, I'm just adding one bit. This is just 1 or 0, and because of this, these two agree, because the expectation of the product is the product of the expectations, because of independence. And so there's a graveyard state again, because as soon as ik equals 0, it stays 0 forever. As soon as this becomes 0, it means that t's happen, and then t's in the past forever. So the graveyard state is basically, it's a graveyard set. It's a set in which this is 0.
When you say random time, you mean stopping time, right?
Nope, not at all. It's not a stopping time. No.
Can't be defined.
Random time. Could, but it's not. I'm saying it's independent of everything. It's a different planet. Okay. So this tau s was a stopping time. That was something carefully constructed along with the process. This is something that's completely on another planet. So this is on Pluto somewhere.
What's the difference between a random time and a stopping time?
Now you better know that for tomorrow. The definition of stopping time is very special.